Oh man, you got it? I'll begin. Oh, for us? It's raining just for us? Oh, for the rest of the day. I'm sorry. I hear what I want to hear. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you bless this class. Help us to tie up our thinking and make sure we leave no stone unturned as we prepare for test one soon coming. Just help the students, each one of them, to finish their homework and to understand each problem, Lord. In your name I pray. Amen. So any questions? Yeah. 5.9, number 72. Sure, you're supposed to find the derivative of the inverse hyperbolic secant of the cosine of 2x. And the domain in question is between 0 and pi over 4, right? Yeah. So what's the issue? Maybe the issue is we don't know how to differentiate, devil's advocate, we don't know how to differentiate this, right? I mean, I don't know how to differentiate that off the top of my head. Yeah. It's in this section, of course, but let's derive it. So y equals inverse hyperbolic secant of x. If I want to figure out how to differentiate this, I take the hyperbolic secant of both sides, right? Hyperbolic secant of y equals to x. Now I can differentiate that. The question is, what's the derivative of hyperbolic secant? Well, even that I'm not sure about. So sidebar, oops, I mean I forgot. What is dd theta of secant theta? That's 1 over what? 1 over cosine, 1 over cosh theta. So that's minus sinh theta over cosh theta, cosh squared theta by the chain rule. And so we got minus hyperbolic secant theta, hyperbolic tangent theta.
Wait, what? How'd you get to the cosh?
Yes, can anyone explain that to him? What'd I do? What is that step? So we're looking at the derivative with respect to theta of 1 over u, right? That's minus 1 over u squared times du d theta by the chain rule.
Okay.
Yeah, so if you don't like that, you could do the quotient rule. But all roads should lead to the derivative of hyperbolic secant being minus hyperbolic secant, hyperbolic tangent. Now, so once we know that, all right, we need to know that in order to make progress here. Now I can implicitly differentiate this, right? What's that give me? I get minus hyperbolic secant of y, hyperbolic tangent of y, dy dx, which is what we're after, equals to 1. So solve for dy dx, which is what I'm trying to figure out at the moment. We're still not to the problem yet, right? Minus 1 over secant, hyperbolic secant y, hyperbolic tangent y. Now, I don't want my answer in terms of y. I want my answer in terms of x. Oh, well, this is already x, right? So what's hyperbolic tangent in terms of x? You know, this seems like a good opportunity for me to introduce my interesting hyperbolic analog of the triangle. So if this angle is x, right, and we've got, this is secant, which is what? 1 over cosh y. So we've got, this helps me to think better. Cosh y is what? 1 over x, yeah? So I can think about this being 1. I can think about this being x. But the thing is, cosh squared, sorry. That's y. I'm an idiot. That's y. Sorry, I was having this very strong cognitive dissonance, something wrong. That was a y. Okay, fine. So cosh squared y minus sinh squared y is equal to 1, right? So that means that, well, let's see, what does that mean? That means if this is 1 over x squared, right? Oh, I'm sorry, I still... My brain is broken again. Oh, man. What's wrong with my brain? Something seems amiss. All right, the triangle's not helping me at the moment. I'm going to have to scrap it and just go full bore algebra. My brain's not working on the triangle at the moment. How do I solve for tang? Right, I mean that triangle thing I was trying to do and failed at just now, that's just a mnemonic for doing what I'm doing algebraically anyway, so I'm not really taking anything away from you, I'm just taking a picture away from you. So, but it's a picture I can't explain, so let's just, for the moment. So what's tang? I mean, I've got cosh is what?
X.
But sinh is what? How does sinh relate to cosh? Right, so sinh y is what? Sinh squared y is cosh squared y minus 1, right? Which here is what? Looks like 1 over x squared minus 1, if I haven't made a mistake. Right? Agree, disagree? So, if I haven't done something stupid, 1 over x squared minus 1 divided by what was cosh y? Cosh y was what? Was 1 over x, right? Now, we're between 0 and pi over 4, right? Not included. So x is positive, right? That's kind of helpful because that means I can simplify this. Maybe I shouldn't simplify it, though. I mean, I'm multiplying tangent y times x, right? Bless you. Let me just, I don't know, I have trouble with decision making here. So this is x times the square root of 1 over x squared minus 1, yeah? Which, because x is positive, mind you, this is the square root of x squared, 1 over x squared minus 1, right? Because this x is what? It's the square root of x squared. This is assuming x is positive. If x is not positive, when I make this move, I have to put a minus up front. All right, continuing. So, I mean, of course, you know, for the sake of this one homework problem, you could use the results in the section to do it, right? But my larger point here to you is we should be able to derive these things. So that's why I'm going through it. I think it's good to go back and remind ourselves how we derive the derivatives of inverse trig functions, because You have had homework on it, so it might come up might come up on the test, right? And besides, I want you to learn how to do it for your own sake also. And so d by dx is what? Minus 1 over hyperbolic secant y, hyperbolic tangent y, and that's minus 1 over what? So we said that was x, and then the tangent is what? It's actually just what? It's the square root of what?
1 minus x squared.
Exactly. Thank you. Yep.
So if we get a question on the homework on the test, like a derivative of sinh x or something like that, you want us to derive it instead of just saying that the derivative is cosh of x?
It depends on the problem. If the whole problem is if like the problem is stated, show the derivative of sinh is cosh, then I would want you to say sinh is 1/2 e to the x minus 1/2 e to the minus x, differentiate it, and show that you get back cosh.
And if it just is
On the other hand,
cosh?
on the other hand, if it just said differentiate and like sinh came up and it was part of a bigger problem, I wouldn't expect you to derive y's derivative of sinh is cosh, right? So it depends on the problem.
For like this problem, we could just, if we know the identity.
For this problem on the test, if I just say differentiate, yeah. I haven't even written the problem on the board yet, but if I just said differentiate that, then yeah, you could use what you know. You wouldn't have to derive inverse hyperbolic secant. But odds are, if I asked that derivative on the test, I probably made you derive it elsewhere. So now, if the question was derive that the derivative of inverse hyperbolic secant is what it is, in the context of that, I would be totally fine with you just saying, I know the derivative of hyperbolic secant is minus secant tangent. Like that, you wouldn't have to show. So it's context. You know, I want details relevant to the question which is asked. So anyway, I'm digressing. So this, therefore, we get ddx. ddx of inverse hyperbolic secant of x is apparently minus 1 over x times the square root of 1 minus x squared. Please tell me that's what's in the section. You double check here.
That's right.
Okay. Phew. All right, but this is how I would work it out. I mean, there are other ways, but this is one way. Now, this is not the question then is what?
Inverse hyperbolic secant of cosine 2x.
Yeah, cosine of 2x, right. So here I do what? Minus 1 over cosine of 2x square root of 1 minus cosine squared of 2x times ddx of the cosine of 2x, right? Chain rule. If I write any more, I will solve the problem, so I'm going to stop. So I'm not sure what, so your question was really more like how would we, did I answer your question? Was your question really about
I messed up on getting to that.
how this is known? I mean, in print,
The cosecant, or cosine messed me up.
yeah, I would say in the context of your homework, you would be completely within your rights to say, in this section, you know, you could say by theorem 5.25, we know that this is true. So with the chain rule applied to the inside function of cosine 2x, we get that, right? Yeah.
What if we don't do that in our homework? Like if we just write down that write it down.
You mean you just do the calculus without saying by theorem 5.25?
Yeah.
Yeah, probably still wouldn't take off points. But I want you to know that's where it's coming from is all.
Okay.
Yeah. Yeah.
Did you multiply it by the derivative of cosine 2x?
Yep, that's what I did.
Oh, right.
I just didn't, yeah. We do not disagree. Other questions? Yep.
section 8.2, number 20?
8.2, number 20, you say. I think I've talked about this already.
Did you?
Yeah. So number 20 and 8.2, I will just give you a hint. Now, I may not have actually, I think I just give you a hint. X cubed e to the x squared dx over x squared plus 1 squared, yeah? Yeah. So here's my hint. Let w equal to x squared, then do a integration by parts to as a finishing blow. So w equals x squared changes the integral. All right, you make that substitution. That doesn't solve the problem, but it changes it into something that integration by parts can be done on. So, other questions? This is a tough problem. The only reason I know that is because one of you asked me about it in office hours, and after about 20 minutes of suffering, I figured this out. Yeah.
So if you're making w equals x over 2, how is that, will that interact with the x to the third? How would you write that?
So dw is 2x dx, right? So if I call this I, since I've wrote that in a poor place, I is equal to the integral of, so w e to the w, that's 1/2 dw divided by w plus 1 quantity squared.
Yeah, that's an x cubed in the numerator.
Yeah, I know.
So W x squared.
Because x dx is 1/2 dw. So I took an x from the x cubed and made it into the 1/2 dw together with the x. I mean, x dx, 1/2 dw. Here, x squared, x. This becomes this. Other questions? Yeah.
Section 5.9, number 36.
5.9, number 36. I can try. So you're supposed to find the equation of the tangent line to the graph of the function at a given point. Here we have y equals e to the sinh x, right? So I'll do it for y equals e to the, I don't know, 2 times the hyperbolic cosine of x, so I don't do your problem exactly. Find tangent through, let's see here, 0, comma 1. So this is like number 36 of section 5.9. I won't, this is not the same problem, but it's a similar problem, right? So the question is, how do you find the tangent line to a function, right? So just a brief reminder, for y equals f of x, y equals to f of a plus f prime of a times x minus a is the tangent line through a comma f of a, provided, of course, f prime of a exists, right? So this is calculus 1 that we know. Supposed to know. We'll soon learn again. I'm not sure. You pick your poison. But here, what's f? So my f of what's dy dx? Or if you like,
e to the cos.
yeah. Yeah, we have e to the 2 cosh x. Then chain rule says we differentiate the inside function, right? Multiply it. So what is that? That is e to the 2 cosh x times 2 sinh x. Oopsie. And I have done something very bad, which is not, yeah, I'm not solving the problem in your homework. That's up for you guys. So this is a related problem, which is not the same. So is this right? Is that actually a point on the graph? If I say that my slightly modified problem here, I'm calling this thing f of x, right? What is f of 0? What's cosh of 0? 1. Yes. So what's e to the 2 times 1? Yeah, it's e squared. I mean, it's e squared, right? So it's about 9, not quite, but so this 1 is totally bogus, right? I was thinking that this thing worked out to 0, but I forgot that's not what it does. So to fix that, of course, that 1 should be e squared to make my problem make sense, okay? So there we go. All right, so here is my f prime of x. So what's f prime of 0? Because we're trying to find the tangent line through 0, comma e squared, right? So what's the slope of the tangent line? The value of the derivative of the point, which is what? E squared times 2 times 0, right? Because sinh of 0 is 0. We should know sinh of 0 is 0 without a lot of thinking at this point, yes? Sure. Or we could figure it out. But anyway, the derivative of 0, which means that this in fact has a horizontal tangent line. My example does, not your homework problem. And so therefore, y equals to e squared is in fact the equation of the tangent line to that function at the point, right? Now, my example went a little bit weird. Let me just do another point. Or how about this? If we go through the point natural log of 2, comma, what? What would we put up there? If we pick natural log of 2 as the x coordinate on the graph and we want to find the tangent line, what's the y coordinate on my graph? What's f of natural log 2? E to the 2 times the cosh of natural log 2. Should you need a calculator to calculate this? You should not. What is the cosh of natural log 2? Yeah, this is 1/2, right? E to the log 2 plus e to the minus log 2, which is what? These halves and 2's cancel, right? So we get e to the 2 minus 1/2. The minus is coming from, not minus, I'm an idiot. I'm an idiot. That should be what? Plus, yeah. The point is minus log 2 is what? That's the natural log of 1/2. Yeah, and I think I'm still,
That's what cost is.
yeah, okay, yeah. So this is 2, that's 1/2. These cancel to give me 1. I've got 2 plus 1/2. With me? So this, of course, is e to the 5 halves. There you go. So apparently, e to the 5 halves. So what's the slope at this point? F prime of natural log of 2. What's the derivative at natural log of 2? My derivative function was e to the 2 cosh of the natural log of 2, right? Times 2 sinh of the natural log of 2. The reason I picked natural log of 2 is because I think it's a helpful arithmetic for us to go through, right? You guys may not have seen, I don't know. So we just worked that out. That's e to the 5 halves, right? And then 2 times sinh is what? That's actually e to the log 2 minus e to the minus log 2. There's a half in sinh that cancels with the 2, right? And that, you say that's 3 halves. AK 3. Okay, so we got 3 halves, e to the 5 halves. It's kind of cool. So that's the slope of the tangent line. Now we can put it together. What's the tangent line at that point? The tangent line at that point is what? Y equals to e to the 5 halves plus 3 halves e to the 5 halves times x minus log 2. And there you go. That is the equation to the tangent line at that point. Any questions about this problem?
We can leave it in that form. That's like further simplified.
That is simplified.
Wait,
I know what you mean, though. No, you do not have to put it in mx plus b form. Why do we put it in mx plus b form? Because it's easy to graph. Yeah, maybe that. I like this form, though, because if I have it in this form, I can immediately read off from this that natural log of 2 comma e to the 5 halves is a point on the graph, and that it has slope 3 halves. Like, the mx plus b, what's the advantage of that? The b has the significance of being the y-intercept, right? And m is the slope. But, you know, this is sometimes called point slope formula. I don't know. But this is an equation for a line. You do not have to multiply it out, no. Kind of like here, if you at some point, so let's just have this talk. All right, ready? So this is not equal to like this we are taught in middle school. This is a horrible, horrible notation when you get to algebra. We do not write this in algebra, right? We must write that. Because this, in our current notation, is 1, depending on how you read this space. It's either 1 or it's just 2 things just sitting out there on their lonesome. I don't know. So we actually prefer to write this as 5 halves. So improper fractions are where it's at, because these are how we do calculations, right? Writing things in terms of proper fractions is a waste of your time in calculus, pretty much. On the other hand, this is this is a kind of improper fraction that we would like to fix, right? Because this we can't integrate, even though it's got x to the 5th x squared upstairs. How do I integrate this? First move, I have to do long division. So I was just talking to another professor. I wonder, how many of you guys actually know long division in here? Who saw long division in like high school? Who did, for more productive question, who did not see long division in high school? So you guys just did synthetic division? Like, this is what I've been told. That is unfortunate because synthetic division only works for what? It works when you're dividing a linear factor. But we have need to divide quadratic or cubic or other kinds of factors. And if all you know is synthetic division, you can't do it. Right? So either you had a bad teacher or you had a bad curriculum. Let's say you had a bad curriculum. Right? That's friendlier. So x cubed, but it's not unusual. Like Dr. Sprano was telling me that, telling me, it's not a word, but he was telling me that you guys are cheated in that regard. So many places don't really teach long division anymore, which is so unfortunate because it's something that we not only need to know, but ultimately you're going to need to know how to generalize it as you go on. So it's quite unfortunate that long division has, for some reason that I don't understand, started to been rooted out of the algebra education in high school here. That's a bad move. Yeah. Oh, what'd I do?
Wouldn't that subtract into negative x?
No, x squared minus x cubed. That's, like apples and oranges. These are.
Sorry, my bad.
Yeah, I know what you're doing, but no. Yeah. And then plus 1, yeah. So that gives me x squared. Oh, I'm sorry. Now I'm a victim of my own notation. I got to pick on what? Just because I write x squared first doesn't mean that's what I need to worry about. I need to worry about the biggest thing, right? Which is that guy. So I should do what? Minus x, yeah? So this gives me minus x cubed minus x, right? They cancel. I get x squared plus x. Then I do what? Plus 1. That brings down x squared plus 1. I take the difference. I get what? X minus 1. Now I've found, so what I've come to here then is the remainder, because this has smaller degree than the divisor, right? And so that tells me that this integral is in fact the integral of x cubed minus x plus 1 plus x minus 1 over x squared plus 1. And that we can integrate, right? This is what? This is 1/4 x to the 4th minus 1/2 x squared plus x. This integrates to 1/2 natural log the absolute value of x squared plus 1. No need for the absolute value because that's positive. And then minus the inverse tangent of x plus a constant. If you're wondering what just happened, to get this, I made a u equals to x squared plus 1 substitution, right? So du is 1/2 x dx. I'm sorry, x dx is 1/2 du. So the x piece gives me the log, and then the minus 1 over x squared plus 1, that's an arctangent, right? That's one of our elementary integrals. Or if you really love trig substitution, you can make an x equals tangent theta substitution.
Wait, if you use the whole term for your u, like the entire denominator, wouldn't that just, sorry, like, so I get that you get 1 over u where you get the ln.
All right. So this is equal to the integral of x dx over x squared plus 1 minus the integral of dx over x squared plus 1. This piece is the integral of du over 2 all over u, and that's an arctangent. Have I said something offensive? And then, of course, that's 1/2 log absolute value view, you know. Yep.
So do you like how you split it up like that? Or do you like to do it without splitting it up?
Which splitting are we talking about?
The XDX on top minus.
Well, I don't see the need for writing that down personally. I mean, these are basic integrals that
Oh, wait,
we've seen
you
in,
do that on top?
I mean, I did it in my head.
Right.
That was, I mean, is there another, can I do this all at once as one integration?
Yeah.
Yeah, I guess, but why would you want to? Right? Why would you want to? When you can have two easy integrals, why have one hard integral? Right? I mean, how would you propose we do it? See, the thing is, I can't make u equals x squared plus 1 my u substitution here if I do this all at once, because I've only got x dx on the one term, right? So I can't make a u equals denominator substitution anymore if I include the -1 in my thinking. I could do a trig substitution. Let's try it out. See what happens. So this is the integral of, tangent theta -1 over secant squared theta d theta, right? So this is integral tangent theta -1 d theta, which ain't bad. I mean, that's the integral of sine theta d theta over cosine theta, although I'm sorry, I think I am violating your ninja way. I have converted it back into, I'm sorry, you may not believe in ninja ways. I watch too much Naruto, has been commented before by me. This is going to be a u equals cosine substitution, so that's minus the natural log the absolute value of the cosine theta, minus coming from the u substitution, minus theta plus a constant, then going back. See, going back hurts a little bit here. Not that much, but if this is theta, and x is tangent theta, this is x, this is 1, this is the square root of x squared plus 1, so that is minus the natural log the absolute value, 1 over the square root of x squared plus 1, minus now theta, well, theta is inverse tangent of x, go figure, right? And then this minus can get absorbed into there, and you can pull the half out. That is 1/2 log of x squared plus 1. So yay, full circle. But again, my initial comment, why? I mean, you can, but do you want to? I think it's easier just to look at it as separate, like divide and conquer. The x over x squared plus 1, u substitution. The -1 over x squared plus 1 is an arctangent integral. Am I not answering? Okay. Sometimes I hear a question, but you've actually asked a different one, and I haven't understood it yet, so I'm always looking for that. But other questions? Yeah.
5.9, number 60.
5.9, number 60. Oh, yay, same section. Ooh. Here we're asked to... This one's a hoot. This looks much worse than it actually is. All right. So here we're integrating and e to the minus x cosh x, right? Now this problem actually has bounds. I'll leave the bounds to you, okay? Is that all right? Is your question about the integration or about the bounds? Who asked this? I forgot already.
I mean, it's definite integral.
Yeah.
But my question is your question about the integration or is it about the the problem?
More towards the bounds, yeah.
More towards the bounds? All right. Then I got to change the problem. Cinch then. So I'll put some quotes on this. It's no longer exactly your problem, right? How would you do this problem? Yeah, and so the question is, what is e to the minus x? What is e to the minus x times sinh? Right. Prince, is it? Yeah, right. So laws of exponents say this is actually what? Integral from 0 to log 2 of what? Of 1/2, right? Minus 1/2 e to the minus 2x. Yeah. And that you can integrate, right? I mean, that's, yeah.
You could factor out that 1/2 to the outside.
Oh, yeah, sure, sure. So this is 1/2 of x minus 1/2 e to the minus 2x, evaluated from 0 to log 2. You like the half came back again. Why is that half in there? What? Right.
Plus,
It would be plus, and why? Why would it be plus? Thank you.
because when you integrated -2x,
Right.
you got -1/2.
Right, so I'm making a u equals to minus 2x substitution implicitly here. So the du gets a minus in it, right? So that's a plus because the negative. The long story short is if I differentiate what I have here, I'd be able to get back to what I have there. Of course, I factored the half out, right? So here, let me factor the half out so you guys can see it easier. There. Should make it easier to see. Of course, then we have to do fundamental theorem of calculus, right? So that's like what? 1/2 log 2 plus 1/2 e to the minus 2 log 2, right? Minus 1/2 0 plus 1/2 e to the 0. Well, so what's that? That's 1/2. Looks like I got a log 2. This is what? Right, this is 1/4. Very good. And then, well, what's this? This is, looks like minus 1/4 from this piece down here. So, I mean, I can simplify that a little bit. What do we got here? We got, I'll just leave it as log 2 over 2 because I'm lazy. And that's what? That's a 16th. What's a 16th minus a 4th? 3/16, right? So. Yep.
When I just found mine, I separated the integrals. I mean, I separated them up into like integral of 1/2 or.
Yeah.
Yeah, 1/2 x. And then,
This should not be your answer on number 60, guys. This is not number 60, right?
and then I did like the integral, and then I used the b subtract a on both parts separately, and then I added them.
Oh, it'll be the same.
It'll be the same.
Yeah, yeah. So like, here, I'll show you. If I have integral of f of x dx plus the integral of g of x dx, right? From a to b, right? Then this would be equal to, by FTC, big F of b minus big F of a, right? Plus big G of b minus big G of A. But you see I can regroup terms, and that's just this. You got options. Mm-hmm. Yep. Other questions? Yep.
But 5.9 over 52.
.9, number 50. Oh. All right. I'm afraid to scare. I'm scared to change that to something else. So I will just have to work on the problem directly. I'm sorry if this takes the fun out of it. Is that right? Okay.
We forgive you.
You forgive me? All right. Integral of hyperbolic secant cubed times tangent. Have I done this already? Oh, wait a minute. I just thought of how I can do it, but not do it. Maybe I shouldn't, though. Should I? How about this? This is the integral of hyperbolic secant squared x times hyperbolic secant x tangent x dx. Yes, no?
Wouldn't it be easier just to convert the hyperbolic tangent to hyperbolic sine? I would think.
I mean,
Or like convert them all to hyperbolic sine.
I don't know. I mean, if I make, I think this is minus du if I let u equal to hyperbolic secant x, right? We just worked that out over here. Derivative of secant is minus secant tangent. So this is minus the integral of u squared du. Integral of secant to the fifth theta tangent theta d theta. Oh no! Check it out. Integral secant to the fourth theta secant theta tangent theta d theta. Voila. This is du of u equals to secant theta, and so this would be integral of u to the fourth du. So, you know, these game I'm playing for hyperbolic secant and hyperbolic tangent, it's much like the same game we play for secant and tangent. What's the difference? The difference is just in a sign, as in SIGN, right? This pesky minus happened to us in the world of hyperbolics, right? In the trigonometric world, that minus is just become a, well, you know, du is secant tangent, right? There's no minus. But anyway. Yep.
For that one, I think I did what he was talking about, where I did, I converted it to sinh and cosh.
Well, we could do that too. Let's see here. So you guys are hopped up on hyperbolic cosine and sine. Is that what I'm hearing? Let's see here. You addicts. Let's see here. I'm sorry, I stopped making drug analogies. Let's see here. This is sinh x dx. We're not cool with that, right? Drugs are bad still? Right? Okay. Yeah. So we've got three koshes downstairs from this one. We've got one kosh downstairs from that one. We got a net of 4 kosh to the fourth. So you guys are like, if you do this, then you're just like, aha, this is the integral of du over u to the fourth, and you're good to go, right? And that's also, that's fine. Nothing wrong with that. I mean, that's another way to go. I'm not opposed. I like it. It's good. What is that? That's minus 1 over 3 u cubed plus a constant, right? Yeah. This one's also what? Minus 1 over 3 u cubed. But notice the, isn't that cool? So the u, this u, and that u, they're not the same, right? They're reciprocal, which is why this is 1 over u cubed, and that's 1/3 u cubed. They're the same answer. One is in terms of hyperbolic secant, the other one's in terms of cosh. Same answer. There are many roads, yes. You just need to pick one. Yeah. How do you know where you're going? You need to know how to differentiate these things, right? If you don't have a clear and command of the differentiation, you can't do the integration, right? The only way I was able to make that secant tangent substitution is because I knew the derivative of secant, hyperbolic secant, was minus secant tangent, right? And the only way you guys knew to make this cosine, this hyperbolic cosine substitution is because you knew that the derivative of cosh was sinh, right? If you didn't know that, you'd be in trouble. And also what was nice for you guys is this idea that you could convert something in hyperbolic secant and hyperbolic tangent to sinh and cosh, right? And admittedly, there are many hyperbolic sinh and cosh, hyperbolic secant and tangent problems that allow quick and elegant solutions in terms of sinh and cosh, but not all, right? For example, if you were to integrate hyperbolic secant x, hyperbolic tangent x, dx, right? And if you did this in terms of, if you do it in terms of your knowledge of hyperbolic secant and tangent, you're done, right? This is minus hyperbolic secant of x plus a constant, right? What happens if you do it in sine and cosine? Sinh and cosh. You're like, you're not really making a very good point because I can still do it, so fine. You can still do it, but my point is if you know the other, then it's already done, right? Not such a big contrast here, though. It seems like converting to cosh and sinh is a good way out if you forget your tangents in hyperbolic secant stuff, in a lot of cases anyway. I don't deny it. Other questions? Yeah. Oops, sorry. What was, maybe. I'll take that under advisement. What was your question? In the front row?
Oh, I had 8.1, number 52.
All right, I'm going to choose which one's easier. Do both. Do both. You guys, I think I am just a machine to do your homework. Let's see here. What was that? 52. 52. Ooh, solve the differential equation. Well, that looks fun. I probably should talk about that. We'll get back to yours. There are some problems in your homework which should, so, if you guys had never seen, there's a problem in your homework about finding the volume of a torus, right? It says find the volume of the solid of revolution, If you never saw how to calculate the volume of a solid of revolution in calculus, what should you do? What's that? YouTube it? YouTube it? You could do that, I guess. But how about you look at the section in the book on solids of revolution, right? Or you ask me a question about it next class so I can work it for you, right? Or I can work some examples like that for you. You just have to ask, right? It is my intention to work those kinds of examples into lecture, but then people ask questions and I forget what I'm doing and stuff happens. So it's up to you to push the lecture back where it needs to be sometimes to be helpful, right? Yeah.
Is there a chance we're going to see like integration radicals or something like on the test? Or like
It's possible. It's in the homework. Let's see here. So number 52. Number 52, dy dx. Dy dx is equal to 4, what is this? 4 minus e to the 2x quantity squared. And we're supposed to do what? Solve this differential equation. I have good news for you guys. We have done nothing for the most part, except for like the tangent line example today. And we did some algebra early on. But by and large, all we've been doing all semester long is solving differential equations. Did you know that? Let me show you. So what do we do? What's our problem? We integrate y dx, and we get that it's equal to, you know, some function f, right? This is what we keep doing. We're given a y, we try to find an f. What does this mean? What's this interchangeable with? This means that dx is equal to what? Y, right? In other words, every time you integrate, you're solving a differential equation. This differential equation corresponds to that integral. So you just gotta, this one, just integrate both sides. So the integral dy dx is equal to the integral of 4 minus e to the 2x, which is kind of scary. Dx. Number 50, what section? This was from 8.1, was it?
Yes.
I should have written that. Sorry about that. So how do you do this integral? I mean, that's easy enough. This is y, right? Yeah, expand, right? This is like at the start of Calculus 1 where they give you those stupid problems. You're like, how on earth do I do that? And it's like you FOIL it out and then integrate term by term. Haha. You know. Well, I don't know. It gives me joy. But so, okay, yeah, now we can integrate. Right? Let me go to your other problem. So that's how we solve differential equations. These differential equations you can solve by integrating. A little bit later in this semester, like much later, we'll talk about how to solve differential equations which also involve both y and x. Like you've got dy dx equals to stuff with y and x. How do you solve that? We have a couple different techniques. We do that right before the final. If I remember right, I pushed that off. I put that like, I think I told you the guys day one, I have test 4 moved up a little bit so that you're not quite as stressed on the final. And then like between test 4 and the final, we'll cover how to solve like more interesting differential equations, which is I think chapter 6 in the book, but we're skipping it and coming back to it later. Number 87. Ah, great. This is a volume question. So we've got the region bounded by e to the minus x squared, y equals 0, x equals to 0, and x equals to b is revolved around the y-axis. So this is a volumes of revolution question. So if I have one bit of advice to share with you on how to do volumes problems, it's draw a picture. If I have 2 bits of advice to share with you on volumes of revolution problems, it's to draw another picture. I think you know what my third piece of advice is going to be. Like you can't draw enough pictures. Just keep drawing pictures. You got to draw pictures. So here we have, where was I? Y equals e to the minus x squared, which is a very interesting function, right? It's a good thing we're not being asked to find the area under this curve. What's the antiderivative of that? It's continuous, so it exists. But that doesn't mean it's nice. It's not an elementary function anyway. So we're supposed to, here, let me draw the picture. So what that thing looks like is, it's like the bell curve actually, right? It's a Gaussian. And I think we're going from x equals to 0, right, which is here. And what was it, x equal to b? And then we've got y equals 0 as another boundary, right? And this is the top. So we're taking this region in here. What are we doing to it? Revolving it around the y-axis. Okay. So that kind of looks like maybe like a router bit or something if you do that sort of thing. Kind of like a bell, chopped off bell maybe. Or maybe just like a bell, right? Actually, it does kind of look like a bell, doesn't it? If you can imagine. So we're rotating around the y-axis, right? So we're trying to find the volume of this thing, roughly speaking.